we're going to end this unit with a quizkin that kind of culminates a lot of what you've learned here and applies it to a real life problem. So here's a four-part question. This is the first part of it. It says a gasoline engine cylinder has a volume of 618 cubic centimeters. The cylinder is full of air at 75 degrees C in 1 atmosphere. So the question is, if the mole fraction of oxygen in the air is 0.19, how many moles of oxygen gas are in the cylinder? Let's solve it. Well, we want to know how many moles, and number of moles is going to be PV divided by R times T according to the ideal gas law. So the number of moles of oxygen should be the pressure of oxygen times V divided by R times T. So this is a partial pressure that we're looking at. Well, according to Dalton's law, the partial pressure of oxygen is going to be equal to the mole fraction of oxygen times the total pressure. The mole fraction of oxygen, they told us, was 0.19. The total pressure, they told us, is 1 atmosphere. So that means the pressure of oxygen in this container is 0.19 atmospheres. So let's start calculating this. Number of moles of oxygen in here is going to be pressure of 0.19 atmospheres. The volume of our container was 618 cubic centimeters, but this has to be in liters here, so that means 0.618 liters. Plug in R, 0.0821 liter atmospheres per mole Kelvin. And then our temperature, that was 75 degrees C, and 75 degrees C is 348 in kelvins. So this works out to 0.0041 moles of oxygen in the cylinder. So building on that, we're supposed to assume that gasoline is all octane, which is C8H18. How many grams of octane should be injected into the cylinder to completely react with the air? Give this a try. I'll give you an answer in a second. We'll need a balanced chemical equation to finish this, so C8H18 plus 2C8H18 plus 25O2 makes 16 CO2, and 18 water is the balanced chemical equation. Well, we know that we're starting out with 0.0041 moles of oxygen, and we want to know how much octane can that burn up. The mole ratio is 25 moles of oxygen will combust 2 moles of C8H18. But really we want grams of octane, so we'll multiply by the molar mass of octane, which turns out to be 114.232 grams per mole. To two significant figures, this comes out to 0.037 grams of octane that are needed to use up that oxygen. The next question says that this cylinder is part of an engine that has 4 cylinders. Each cylinder undergoes the combustion reaction, so it's going to burn up that amount of gas, every 2 revolutions of the engine's output shaft. What mass of gasoline is burned for each revolution? Well, I don't really know how to do this, so I'm going to use the factor label method to see if I can. 0.037 grams of octane, and I want to know how many grams are burned per revolution, but this is grams per combustion. It told me that there is 1 combustion every 2 revolutions for this cylinder. So that means that's how many grams are burned in every revolution. It works out to 0.019 grams per revolution. Now that's per cylinder, and it said this was part of a 4-cylinder engine, so I'm going to multiply that by 4, and it tells me that every time the engine goes around once, I burn up 0.075 grams of C8H18. Next problem. The density of gasoline is 0.7036 grams per milliliter. The question is, what volume of a gas tank allows the engine to run at 2200 revolutions per minute for 4 hours without running out of gasoline? Let's build on this, and again I'm going to use dimensional analysis. 0.075 grams of octane per revolution. And I know that I'm going to do 2,200 revolutions per minute. So that tells me how many grams are going to get burnt per minute. And I'm going to do this for 4 hours. Now, hours and minutes don't cancel, but I can convert because I know that there are 60 minutes per hour. So now I'm rid of time. This tells me how many grams are going to burn total in 4 hours. But I don't want grams. I want volume for my gas tank. So there's 0.7036 grams of octane in every milliliter, it says. So this will tell me how many milliliters my tank needs to be. But milliliters is probably not how I'm going to measure a gas tank. So I'll convert this to liters because that's a bigger unit. So there's 1,000 milliliters per liter, and that's where I'll end. 2 sig figs in my calculations all through here. This ends up being 56 liters. 56 liters is roughly 15 gallons. So that's reasonable that a gas tank would be about 15 gallons for a 4-cylinder car.